Okay, here we have a quick introduction to what are called separable differential equations. Not all differential equations are separable, but when you have one that is, it can work out rather nicely. Let's start with a really simple concept, and that is that we're looking at the rate of change of a population. What is a population growing over time? So that's the dp over dt, the rate of change of a population over time. Suppose we make the assumption that it is proportional to the population, that as the population is bigger, the growth is bigger. If the population is smaller, the growth is smaller. So it's very, very simple in concept. We can write it like this: some constant of proportionality, all right? Well, with differential equations, we want the population and the time to be able to be written as the form of like some time function and then some population function, and that if they're written in such a way that we can either write them as multiplication or as a fraction, and they can be then separated out through the idea that this is really a limit of two quantities that are changing. We have little bits of the population broken down over little bits of time. It's really a limit, but we can think of it as a fraction. We can write this then as dp dt is equal to k over 1 over p, and thereby sort of separating them into a fraction where these are diagonally opposite. Visually, that's one way to really think of it when you're breaking these down. You could also just think of it as, well, I can go up here and I can divide both sides by p, and I can write this as 1 over p dp is equal to k, if I multiply both sides by dt like this. And once we separate them out, then we can integrate both sides. We can integrate this side with respect to the p, integrate this side with respect to t. Well, this just becomes the ln of p, and this side becomes just kt, like that. There's going to be a constant added to both sides, but just for simplicity's sake, whatever constant we might add to this side, we'll just bring it over here, and we'll have one grand constant over there. Okay? Well, when I see it like this, I'd love to get that p by itself. So if I take and make this the exponent for e, that will be our identity that will just translate this into a form that we perhaps will recognize, that p then is equal to e to the kt. Well, if you're adding a plus c, that's no different than just multiplying it by e to the c, because of course we'd add exponents. And this is just a constant. So we can really write this as p is equal to a e to the kt. Okay? So if we had some initial condition that suppose p at the starting of recording the population would be, I don't know, 120 units of bacteria or something that's growing, sort of, we can make the assumption that's growing continuously. Well then, if we plug in 0 here, and we know it's equal to 120, clearly a here is 120. So now we have a model for this population growing, 120 e to the kt. If we had a second fact that at some predetermined point we could measure the population, say 5, now the population of bacteria 5 hours later is, I don't know, 1,000 or something like that. Okay, we could then solve for k. We'd say, well, 1,000 equals 120 e to the 5k, because it's been 5 hours later if this is an hourly growth rate. Well, I can just do the math. I can solve for that. I divide by 120, cancel a 0. I could just simplify that if I wanted to 50 over 6 or 25 over 3, and then take the ln of both sides, and I'll see that k then is equal to the ln of 25 over 3 then divided by 5. Okay? And then that would give us our growth. Well, that will be like a percentage, just like an interest rate that we could then use to further predict the population at a later time. So this is the incredible, awesome power of separable differential equations. Okay? So here are 3 quick examples. Let's say we've got y squared plus xy squared then times y prime equals 1. Well, how do we make sense of that? Well, what our goal is to write it in a form that we can recognize. So I'm going to write this as dy dt. So our variables are y and t. Can I separate this? Yes, I can. I can factor out a y squared, and I get 1 plus x, and that's then in front of this. So if I simply multiply both sides by 1 over x, I'll be able to get this equal to 1 plus x, And then if I multiply both sides, how did I get, I get dx. That's supposed to be a dx. I wrote dt from the last problem, dt, dx there. And then on this side, I've got y squared still, and that's gone. So now I just integrate both sides. Okay, so when I integrate y squared, I get 1/3 y to the third equals, well, this is ln again, 1 plus x, and then I'm going to have plus c. Okay, well, if I want to get y by itself, I could say then y is equal to 3 times the ln of 1 plus x plus c, and then take the cube root of that, and I will have a simple solution. All right?